Yeah, so my presentation today will be a little bit more high level because not so much maths going on. But I think like a good start would be to do a very quick recap on Sumcheck and GKR, because today I'm going to like briefly just share about like ZK bridge, which uses part of this like Sumcheck and GKR. So yeah, let's just do a 5 minutes quick recap. So basically, Sumcheck is like the prover wants to prove like a multivariate polynomial of like x, maybe x1, x2, up until xn, and so it'll be like maybe if it's a tree, so we'll define like the number of this multivariate polynomial as L. Okay, so L is equals to, oh shit. So L is equals to the number of variables in this polynomial. Okay, so it will be like some computation up until like order combination. I'm sorry. So
the last one XL or XN.
Oh yeah, okay.
There should be L.
Yeah, it's L. It's L. Yeah, number of variables. Yeah, number of variables L. Yeah. Good point. Okay, thank you. So how it works, how the protocol works is like the prover will compute the partial sum. So it computes the partial sum of, let's say, G x1, which is like just substituting this this first variable as x1 plus equals to, okay, and then it will take in a random challenge from the verifier R, random R from the verifier. So this partial sum will be sent to the verifier. It takes in this random challenge, put it into X, and just do the evaluation, right?
This example is 1 L equals to 8 or
1 equals to, sorry?
L equals to 8, right? So you only have 3 numbers for
3 number is L equals to 3. So in this example, it will be L equals to 3.
How is that? Because in the F definition, there are only three numbers, 0, 0, 0. So literally means that L equals to basically 8, right?
L equals to 3, right? No? L is the number of variables. L is like the number of X. Number of X. But the actual computation.
Here is L is equal to 8, right? Because you only have 3.
Yeah, so 2 to the power of L equals to 8.
Yeah, okay.
Yeah. So the actual computation that needs to be done in order to calculate this H will be 2 to the power of L.
yeah.
Yeah, in this case, yeah.
L is a boolean.
No, X takes a boolean.
Does it needs to be boolean?
No.
You can
Okay,
convert
no,
it
X
to
Yeah.
is a field element.
Yeah.
Oh, so then it's not 2 power 3, right?
No, but in this case, right? So
Yeah.
in this case.
Let's define L, X is.
I think all
Yeah.
xi are Boolean variables.
In this case, yes.
In this case, yeah.
And the whole f is a multilinear polynomial in Boolean variable.
Yeah, exactly, yeah.
Wait, can you repeat that?
Multilinear polynomial in Boolean variable.
That sounds very targeted.
Multilinear means that
Yeah, I understand what it is, but like, what do you mean in this context?
So X
what
all
f
boolean.
is
Okay, so in this
X
case,
is
not
a matter
linear.
of 0 and 1.
multilinear.
Yeah.
stopping it before it starts.
Oh no, yeah. Go on the discussion. I like discussions.
Yeah.
What is happening is that you create this gx1, right? So you're summing over all, you take x1 as the variable and you're summing over
Yeah.
all the possible value.
Exactly, yeah.
X3.
So only the x1 is left open.
Okay.
So only the x1 is not evaluated, right? If that makes
Yeah,
sense.
here's the I think easier to understand because right now we just do folding.
Please, please, please.
I also want that one. Everyone should have.
Yeah, I think currently just we just leave this x as here, just because right now we're just folding to instantiate x with a random number. Actually, we fold eight entries. Sum of 8 entries folding to sum of 4 entries.
Yeah.
So the point is just that like the verifier don't want to replace all 8 value of 8. Right? Just like
The verifier doesn't want to compute like all this computation.
value.
So that's why the prover sends like this partial sum.
Okay.
And the verifier basically, in order to evaluate, they just need to compute like G0 plus G1, which is substituting this, right, is equals to H. Right?
Yeah.
Because this is the partial sum that is passed on to the verifier. So basically they only need to, instead of like in this case, instead of calculating like 8, they just need to calculate like 2
So
operations.
it's like the prover just saying the polynomial complement and then the verifier will just open at 0 and 1 and compute.
Yeah.
Okay.
Yeah, exactly, yeah. Yeah, so the verifier send this random challenge and then do this evaluation to make sure it is indeed what the prover claimed it is to be. And we repeat it for all the variables. So we repeat it L times for all the variables. Like this is only for step 1. This is step 1 of doing it for x1, right? And then so the prover will repeat this process of like forming this partial sum for gx2, and then
But wouldn't the verifier compute the G0 and G1 before saying R? Right?
Verify just need to verify.
yeah,
Yeah, but like, like the prover sent Gx, right? And then the verifier
GX.
just
Yeah.
Yeah.
That's right.
And then the verifier compute at G0 and G1.
yeah.
Wouldn't that happen before the R, like the random R thing?
Alright, good question.
Try this.
Oh no, it's fine, I think.
Yeah, very good question.
Yeah, good question. Okay,
Good question.
I
Why the other is
I don't get it. Okay.
I think it can be done anytime, right? Like it doesn't matter, right? This in this order.
I think yeah. Here's thing I can answer your question because in the implementation because the degree of x equals to 1 or 0 or 1, right? Because it's multilinear polynomial, right? So here instead of sending gx to the verifier,
Yes.
the prover actually send G0 and G1 directly to the verifier.
Oh.
Right, so by polynomial interpolation, the verifier can evaluate GR by using G0 and G1. Right, because it's a linear, right? Gx is a linear polynomial, right? So in implementation, it's just the prover computed, prover does not have to compute. Prover just send G0 and G1 to the prover.
Oh, so in this case.
In this case, and this verifier will use the tool to evaluation to compute the GR.
Okay. But doesn't wait? I think verifier doesn't compute GR, right?
Sorry?
It sends R, so that prover compute GR.
Yes, prover has to compute GR
But verifier also has to compute gr. Yeah.
Verifier also.
Oh, they compute as well.
Yeah.
So that they can do the comparison, right?
Yeah,
Like
okay.
yeah.
Oh, okay.
Yeah, so that they can make the comparison whether the value that is computed by the verifier is equals to the value that's sent by
So
the
the
prover.
order doesn't matter, right? Right? Is that the conclusion?
Yeah, I think so. I think
What conclusion?
The order of like.
the order of when this
Computing is?
yeah, this step, yeah. Yeah, I think it doesn't matter.
I think it's a I think it's equation for verifier.
Mm-hmm.
Yeah.
Yeah.
Okay.
Yeah, you can add a question mark here, so make
Oh,
sure
okay.
that
So
it's
that's the- That's the proper notation. Okay. Thank you. Yeah. Go on.
Oh, okay. So the prover just try to prove is equal to h, right? The whole.
Yeah, exactly.
I think the first equation we should like sum. The
What?
first equation h equal to sum of all f, right?
Yeah. Oh, you mean this one?
Yeah, there should be
Okay.
sigma over all f, all x, yeah. Sum
Or
x.
L.
Oh, now that makes sense.
Sorry, I'm not a mathematician, but
Now that makes sense.
okay.
Sum check, right?
Okay, yeah. Good point, good point. Sure.
Wrong from day one.
Okay, so is there any more questions? So basically, yeah, the prover will repeat the process of computing a partial sums, leaving x2 the open one, and receiving a random challenge from the verifier, and then doing the same for this, like doing GR, up until it reaches the last variable, which is L in this case. So because there are L variables in this like multivariate polynomial, a Sumcheck protocol means it has to go through like L elements until it reaches the last. If that makes sense.
And when you go over the last step again, just make sure like you finish all like. So when you go to the GXL, right? Like what was the last concluding step?
The GXL. You mean here?
Yeah, it continues like this until the end, right?
Yep.
What does the end look like?
So GXL will be like F. All these previously have been evaluated by the random. So like R1, R2, and XL.
You, what is you?
Sorry, it's R. It's not U. Bad handwriting. So like the the random challenge by X. Sorry, yeah. I'll write it better.
What was that?
X.
Oh, alright,
Yeah. Yeah. Is that correct? Am I doing it wrong? Yeah. And compute it, get this G RL, and then again check whether it equates to the H. Does that make sense?
Oh, so the verifier compute GRL by themselves.
Compute what? Sorry.
Oh, GR, okay.
GRL. So basically, the verify throughout this entire protocol, the verifier will need to send L random challenge to the prover for L rounds.
Yeah.
Yeah.
And I think you said earlier that Sumcheck try to like instead of making verifier compute everything, right? Like 8 terms.
Yeah.
It just now compute just the last term.
So it needs to compute like, I think the complexity is O of L. Yeah. This is the complexity for the verifier. Because, so for the prover, it will be like O of 2L, right? This is the complexity for the prover, because if you look at this, if it's like a 3 variables multivariate polynomial, the prover will need to compute like 8, because that's all the combination of it, right? But for the verifier, it only needs to compute like this thing at each round, right? So, but it needs to compute like L rounds. So at every round, the verifier needs to evaluate whether the partial sums is equal to like H. So yeah, so it's actually like O to the power of 2L. because it needs to compute like both of this, but it's like L. Does that make sense?
What's the last step is doing?
The last step of what?
GRL.
Equals to what?
Yeah.
Equals to substitution of this into RL. So again, it will be like a G0 plus G1, right? It will be like F R1, R2.
Here I just a small suggestion.
Yeah.
Because this GX is different from here G, so probably you have you better add a subscript here, for example G1.
Oh, okay.
G3, right?
Yeah, so these are different partial sums. G1, yeah.
Here G1, G1, G1.
Yeah, G1, G1, G2, GL.
L, right?
Yeah.
And GL, GL, GL.
Yeah. Yeah. So
And here, TL.
GL.
You get 1 mark minus
Yeah. Does that make sense? So it evaluates whether
So when you modify this OL, like just modify that G1 0 plus G1 1 is equal to H, right? And like maybe that L time. So
Yep.
That main combination. Okay.
yeah, so the verifier do this at every round. And by one round I means like one variable.
One variable.
Yeah, it slowly moves to the last variable. Yeah. Oh. It's alright. Okay. So yeah, so that is like, maybe I'll rub this off. So that is like the Sumcheck, right? The quick recap. And for like GKR, basically GKR they just use like Sumcheck to do the computation, make the circuit into like multiple layers. So each of these will be considered like perhaps layer 0. Oh shit. Ah. Oh, 我这边还有一。Is this better? Yeah. Maybe blue. Oh shit, this is permanent marker. Holy shit.
with normal markers.
I will change that. 给你这个。
拿那个酒精，
Yes.
你刚
我拿
酒精。
Try you just overlap it with normal markers.
Oh, okay, it's okay. 还有这个。
把那支笔拿走。
拿走了。OK。
Okay. Yeah, so GKR, what the fuck? Not even one is working.
Another place, I think that one should be there.
刚刚那个可能是有酒精跟。
Oh, okay, okay. The blue one, is it? Okay, okay, makes sense. Okay. Yeah, it works, okay. So GKR, you just split the circuit into multiple layer, right? And then you do the sum check for each layer. So you evaluate all possible combinations that could go into this. Let's say this is like a plus, like a minus gate. If you extract, if you don't look at everything below it, if you extract it, like it's just 2 gates. let's say like this is like V1, V2, V3, V4, and then this is like output V5, V6, and basically you will get like V1 plus V2, V1 plus V2, so the output V5 will be like V1 plus V2, V6 will be like V3 times V4, and you can just make it into all possible combinations, which means you can like evaluate this as a multiplication gate, so which is like 1 plus 0. So this is the multiplication gate of like V1 plus V2. So I think a better way of writing it is sorry, this is the times. Yeah, so just like this part is just the addition gate, this part is like the multiplication gate, and you do it and form this into, yeah.
So GPI is the way to break down CK circuit gate into layers so that you can do like Sumcheck already.
Yeah.
Is the protocol to decompose CK circuit?
Yeah, I would say so. I think it's like a circuit, and you like the verifier only basically needs to know the output and the input or the input layer, and then what it will do is the prover will compute the sum check of the output, the sum check of the layer 0, which needs to evaluate to the output, like the sum of all these combinations we need to evaluate the output using a claim input. So the prover will just claim like certain input values for this, which is still untrusted because the verifier doesn't know the input value to this. But this claim input will be the claim output of the beneath layer, right? So this will be the claim output. And then the prover will again use the Sumcheck protocol to make sure that all this combination evaluates to this claim output. And again, the prover will have another layer of claim input for this layer. Right. And this claim input is also the claim output of this layer. And up until the final layer where the verifier will be able to, like this input is public to the verifier. So
Oh, I see.
so the verifier will be able to evaluate the sum check on the last layer, and which means that if it's correct, then it also propagates up, right? Like the output is also public to the verifier. So these are all just like the intermediate layers of the circuit, which all this input and output is not public to the verifier, but that's okay because basically we just need to evaluate the correctness of the last layer and first layer and make sure that these are the same.
So the input always public to verifier?
Input? Yeah. Yeah.
Okay, in the very beginning, GKR protocol, in the original GKR protocol, all the input are public.
Yeah.
So GKR was designed for verifiable computation only. And from CMT 12, the paper, and the authors using GKR protocol to make Z snarks. So it allows that the partial part of input can be witnessed. Yeah, and the prover may commit to the witness in front of before that protocol, GKR protocol. And at the last rung, the bottom layer, so the verifier will ask the polynomial oracle to do do the partial evaluation and combine the evaluation from the public to the card.
Okay. Thank you. Yeah.
So how it look, how does GKR use, how is it used in like normal SNAR, or is it like the equivalent of like the tongue, like
Okay, it's a,
like circuit, like computers, whatever?
it's another line of work.
Right.
Another technology, core technology for building SNARs.
Okay, so it's arithmetic. It
Different arithmetization.
okay, but it's still the arithmetization category.
Yeah.
Okay.
Yeah. Yeah, that's just a quick recap on on Sumcheck and GKR. Yeah, so I think like it's interesting because so I'm reading this paper called like ZK Bridge, where they use the Sumcheck and GKR protocol to do like distributed computation on the state of a blockchain. So I guess I can just briefly like walk through about how this is used in an application context. Yeah, so, but I guess like just before just that, like essentially like how does a bridge work? Like another quick 5 minutes intro. It's like, yeah, that's like a blockchain C1, right? Like the source blockchain, and this is another blockchain, right? And you have some smart contracts on, let's say like smart contracts on this blockchain, where you want to prove certain state of the first blockchain on this. So for example, if it's like a token bridge contract, you want to prove that some sort of tokens have been locked in like a contract on C1 so that you can mint a wrap or like alternative representation of the token in C2. So there are a few approaches, like using some sort of like external validator to sign to make sure that this is indeed correct. But for today, I'm going to just talk about ZK Bridge, which they hope to use like the consensus mechanism of chain 1 to prove the state of this. So how they do that is they use like an on-chain like client. So like on-chain like client. And is everyone familiar with how like client works? So a full node is like a full node is the node that has all the data of all the transactions of the blockchain, right? Whereas a light client, let's forget about the on-chain part first. The light client is someone that only has access to the block headers, but didn't have the block body. So what is contained in the block header? It depends on which blockchain. Like for Ethereum, it will contain like timestamps, but more importantly is the state root. So in Ethereum, there's like 3 main root, like the state root, the transaction root, which contains which is the Merkle. So all these are like the Merkle-Patricia tree, and state root contains all like the account balances of different addresses. Transaction root is like the Merkle tree that contains all the different transactions, and there's a receipt tree, which contains like the event logs and stuff. But anyway, I think so. This is what is contained in like block header, and for smart contract on the second chain, they basically just need to have access to this block header in order to prove the state of this on C1. And the reason is that with this block header, so let's say if in C2 it has the state root of like C1 or something, like the block, okay, maybe not just, yeah, like let's say it's the block header of C1. And with this, anyone can provide a Merkle proof in order to prove the state of something on chain 1, if that makes sense, because all these are just Merkle tree, right? Like state root are just Merkle tree. So if someone wants to prove that a particular like account balance or particular state like storage slots of a smart contract in this chain, So let's say the storage slot is stored in this position. The person will basically just need to provide like the adjacent Merkle path in order to prove this. So if the block header, if this root is committed here, then to prove the state of this, someone just need to provide the sibling nodes of the Merkle tree in order to prove like the existence of this. So that's just like how Merkle tree works. So normally like light client, if it's a normal light client, they actually participate in the gossip protocol of like the blockchain. But if we want to put this light client on chain, like become inside a smart contract, so that we can access like all the state root, right? So that we can access this, like anyone can provide like this Merkle path in order to prove like a certain state of this thing. It will be very expensive because how would the light client sync between the issue is how would the light client sync between blocks, right? So you have like block like 0. Now you want to sync it to block 1. How would you do it? Like you could probably pass in all the transactions that occurs between block 0 and block 1 in order to prove the correct state transition of the root. But if you do that verification on chain, it will be very expensive. So how they do it is in Ethereum, or I guess not just in Ethereum, but in many blockchains, the validator will sign on the block header. So there's a bunch of different validator sets, right? Like a few hundreds, a few thousands, or whatever. They will sign on this block header, make a signature. So they make a signature on this block header, and in order to verify that a block header is indeed correctly added, you just need to verify the signature of like the validators. So in Ethereum, they have this thing called like sync committee, where for around every 1.1 day, like 512 of the validators will be chosen to sign on this block header, and that's how you sync. That's how you sync the block header. So if like more than 2/3 of this validator, they sign on this block header, then it's kind of accepted as like a valid block header. So this is useful because it allows the light client that doesn't listen to the gossip protocol of the blockchain to be able to still sync to the latest block header by just validating that 2/3 of this validator actually sign on the block header. If that makes sense.
So they just look at like, oh, this block header got signed by 2/3 and accepted.
Yeah.
Oh.
Yeah. So these are like randomly chosen, by the way. Like every 1.1 day, a different set of sync committee will be chosen, and it's randomly picked. Yeah.
This is different from block creation, right?
Yeah, this is different from block creation. So block creation, this is not involved in like the block proposal or anything like that. This is just in order for the light client to be able to make the state transition from block 0 to block 1 and block 1 to block 2 and so on. So they just need to check like, so when a new block header is proposed, they just need to check that the block header of this is signed by 2/3 of the sync committee.
But that's still immediate delay for the main blockchain because you know you just create like block, right? And then the line and then to wait until 2/3 agree on this block first. Okay, so they're going to delay. Yeah, for sure. But
哦，这个是好。Oh no, no, yeah. Yeah, he explains better. Yeah, yeah. So basically, like I guess the idea of the ZK bridge is that in order to prove that, so the aim of the of this contract is that it needs to keep updated to the latest block header of chain C1.
I got a question.
Yeah, go on.
There's no really ZK to it, right? It's all public.
Yeah.
Thank you.
Yeah. It's not ZK.
Yeah, okay.
Succinctness of, okay.
Yeah, but what about the Merkle proof that you
The Merkle proof? Sorry, what was the question?
the Merkle proof that you need to prove the state, but that is not ZK yet.
Yeah, it's not ZK. Basically, I think the whole thing doesn't have ZK involved.
It's for marketing.
There's no zero knowledge. It's only for the like succinctness property of that. Sorry? Oh, okay. Oh, they do it in ZK. Okay. I see. Yeah, so basically the idea is that you just need to have like need to sync the latest block header in order to prove a state of this. So you need to keep this like maybe this is like block I. We need to keep updating it, block header like I+1 and so on and so forth, right? Just keep updated. And in order to prove that this block header is inserted correctly, we need to check like it is signed by this. This is just for the Ethereum case, but it could be like for Cosmos or whatever to sign on the block header in order to be considered valid in this. So that means they'll need to do a lot of signature verification. So for example, in the case of Ethereum, if it's like 512 validator, they'll need to do a lot of signature verification in order to accept a new block on this smart contract. And it will be very expensive. So I guess 512 is like already a smaller subset, but if it's like for other blockchain ecosystem, they might use the entire validator set for the signature, and that's a lot more signature. So, so I guess this is where like the Sumcheck and GKR part comes in. Is that they just try to parallelize each signature into a different part of the circuit. So, like let's say, what's the best way to draw it?
So, because the last aggregated what they're, so I'm not sure what subject. So I don't think CK Bridge uses this for the sync.
They don't.
I don't believe so. I think they've got their own set of validators they do it on. But like they're kind of vendor because they think they'll prove full through consensus because the field aggregated.
Yeah.
You don't have to check one signature, but you do a lot of work to like aggregate all.
Yeah, exactly. Yeah. So I think they actually use the example of like Cosmos to Ethereum, because that's the one that is expensive. Yeah. So how they split it into the circuit is that they try to parallelize the signature verification. Yeah. So you can think of like this as similar like to the GKR protocol, right? Except that this will be like signature 1, signature 2, signature 3, and so on and so forth. And then they delegate this computation to different provers. So prover 1, prover 2, prover 3, and so on and so forth. So each one of them will do all this computation differently. But they also use the Sumcheck because, again, this can be divided into like different layers, right? So this will be divided into different layers. And then each layer, one of this prover will just do part of the computation. So if you look back at this like equation, instead of, let's say this has like 2 to the power of L computation, so it's like 8 if it's 3. We will split this into like different parts that are done by different provers, and they will just do each of their partial sum computation, and then they pass this to a master prover. So like there's like a master prover which aggregates all of this proof. Like we are just looking at one layer right now, right? Okay, so ignore like the bottom one. We're just looking at the first layer. So every of this different prover will do their partial sum computation, pass it to the master, and the master prover will send it to the verifier and get the random challenge from the verifier. So it will be similar to what we did just now.
So just want to clarify, so
Yeah.
that tree, the leaf, each node of the leaf is the signature signed by validator, right?
So this is just, I guess, just the encoding of the signature verification circuit into like something. So I don't exactly understand how they maps like a signature verification to this. I guess that's like how you write on a DSL or something like that.
Not
Yeah.
DSL. Just the,
Okay.
Rust code.
Okay, whatever. What?
Okay, so each,
I think C++.
C++ code. Oh, okay. C++.
Okay, yeah.
so each tree is the circuit of that signature one. So
Yeah, exactly.
And the prover.
And they're identical circuits because all the signature verification is just the inputs, but they just parallelize that computation.
So each prover is each line client, right?
No, this is nothing to do with light client anymore. So the light client is just a smart contract in this case. Like we don't really have an actual like traditional light client that listens to the to the gossip protocol of the blockchain. It's just a smart contract. So this prover is just so in ZK breach case they have a relayer network that do all this proving. So they will do all this proving, prove that the block header is indeed the correct block header, and then post it on chain. And then the verification is on the smart contract as well. Yeah. So yeah, I think the idea is that. So instead of like if you remember just now, like the proving time is like O to the power of 2L, right? So depending on how many provers you have, let's say you have like n provers, like the proving time will be like just divided by n, right? Yeah. So yeah, I guess the motivation is just to like speed up the proving time. Yeah. And make it faster. Yeah, so once this is proven, then the relayer network will just insert this block header in the smart contract, and anyone can prove a state of this like blockchain 1 using like this Merkle proof thing. Yeah. Okay, yeah, I think. Huh?
Sorry, my bad.
Yeah. Okay, yeah, I think that's mostly it, I guess. Yeah. Okay, thank you.